This is lecture 7 of condensed matter physics. I have been using solid state physics and condensed matter physics interchangeably. So I hope you understand. In this lecture, what I want to do is obtain the specific heat for metals and its temperature dependence using free electron model. So let's begin. I had argued earlier that Cv is proportional to T, and this was because of Pauli exclusion principle. And what we want to do today is derive an expression for Cv using free electron model. For this, what I need is that the energy of the electron gas at temperature T, which is given as integration 0 to infinity of energy E. At energy E, energy is obviously E. Then there is this density of states epsilon E, and the probability of occupation of that level, which is given as F of Fermi-Dirac at energy E at temperature T. This is total energy of electrons at temperature T. And then Cv is going to be calculated as du by dt, which will be equal to 0 to infinity dE epsilon dE partial F partial T Fd, because this is the only temperature dependent quantity. So if I want to calculate Cv per mole, then this dE is density of electrons per mole. So our job is to calculate this. What we need therefore is these dE and all that for three-dimensional electron gas and the Fermi-Dirac distribution. So let me take them up one by one. We have already learnt that for a 3D electron gas, and we are taking them to be free electrons of density n, this is number density, we have the Fermi wave vector kf, which is 3 pi square n raised to 1/3. Then we have Fermi energy epsilon f, which is h cross square kf square over 2m. And then we have the density of states per unit volume, which is, I can write as 3 by 2 n epsilon over epsilon, where n epsilon or Ne is the number of electrons filling levels up to energy epsilon. And we had seen earlier that Kf is of the order of 10 raised to 10 meter inverse, epsilon f is of the order of 5 to 10 eV, and density of states per unit volume is of the order of 10 raised to 28 per eV. So, this part we have covered. Now, I want to spend some time on the Fermi-Dirac distribution and its derivatives, because that's what we will be using in this lecture. So, Fermi-Dirac distribution F for energy E at temperature T is written as 1 over e raised to E minus mu over kB T plus 1, and this is for non-interacting electrons. Which is precisely what we are considering, because we are taking electrons to be having no interaction. Mu is known as the chemical potential, and it is temperature dependent. I'll show you in a minute how it depends on the temperature. And mu at T equals 0 is equal to epsilon f. It also represents the change in the energy as the number of electrons are changed. So, at T equals 0, if I were to plot F E 0, the levels are filled up to epsilon f, and the distribution appears like a step function. This is 1 precisely up to epsilon f, and then 0 afterwards, and all these levels are filled. So, here this is equal to mu. As you increase the temperature, initially for low temperatures, the distribution becomes like this and spreads out. This is epsilon f, and the value at epsilon f is exactly 1/2, 1 on top, and here is exponential. We will see in a minute how that happens. And then these levels out here are vacant, and all these electrons go here. If you increase the temperature further, here was epsilon f, the distribution may become something like this, so that the value 1/2 is at a point below epsilon f, and you can see from the expression this is mu, because at epsilon E equals mu, the occupation is precisely 1/2. This is F E T, F E T. So, as the temperature is raised, the chemical potential shifts inwards, it becomes below epsilon f. So, what we have learnt is that F E T is 1/2 for E equals mu, and mu is temperature dependent. It is less than mu 0 which is equals epsilon f, and mu t, and this I'll give you as an assignment problem, comes out to be epsilon f minus a constant pi square over 6 kBt square over epsilon f. So delta mu as a function of temperature is minus pi square over 6 kBt square over epsilon f. It changes quadratically with temperature, and d mu dt is equal to minus pi square over 3 kb square t over epsilon f. If I write symbolically that epsilon f is equal to kb Tf, just to define Fermi temperature Tf, it is not the real temperature of the gas, but just to define a number, then you get d mu dt as equal to minus pi square over 3 kb T over Tf. So it's of the order of T over Tf. Recall from our estimate of epsilon f, Tf is of the order of 10,000 K, so T over Tf is much less than 1. More importantly, the derivatives of Fd epsilon t is important in our discussion, and that's what I'm going to talk about next. So F Fermi-Dirac Et is equal to 1 over e raised to epsilon minus mu over kb t plus 1. So partial derivative with respect to energy is going to be e raised to epsilon minus mu over kBt times, so with a minus sign, e raised to let me just write it again. Partial f over partial e is going to be equal to minus 1 over kBt times e raised to epsilon minus mu over kBt divided by e raised to epsilon minus mu over kBt plus 1 whole square. And partial f over partial t is going to be equal to epsilon minus mu over kBt square e raised to epsilon minus mu over kBt divided by e raised to epsilon minus mu over kBt plus 1 whole square, and there is an additional term plus d mu over dt 1 over kBt times this exponential terms e raised to epsilon minus mu over kBt divided by e raised to all this plus 1 whole square. So there are two terms in this. What I want to focus on for the time being is this exponential term. Which is common here. So focus on e raised to epsilon minus mu over kBt divided by e raised to epsilon minus mu over kBt plus 1 whole square. Notice that epsilon minus mu over kBt is less than 0 for epsilon less than mu and is greater than 0 for epsilon greater than mu. Let me call this f prime as factor rather than writing it again and again, minus mu over kBt divided by e raised to epsilon minus mu over kBt plus 1 whole square. Now for room temperature, kBt is of the order of 25 MeV. We had obtained this number last time. So if epsilon minus mu is less than 0 and epsilon minus mu over kBt is of the order of 5, implying that epsilon minus mu is of the order of 125 MeV, then f prime would be equal to e raised to minus 5 for epsilon less than mu and again e raised to minus 5 for epsilon greater than mu. You can check that very easily, and e raised to minus 5 is of the order of 1 over 50. That's 0.02. So from the value of f, which was 1/2, or at E equals mu, it's 1/4, 0.25. The value by 5 comes out to be, this is f prime, 0.02, which is 1/10 of the original value. So the factor f prime actually has a character like this, where this peaks at epsilon equals mu and then goes down. Let us see how sharp this peak is. So I had said that f prime is roughly 1 over 50 for epsilon minus mu over kBt equals 5, which is 125 MeV, and mu is of the order of 5 MeV, which is 5 eV, which is 5000 MeV. So delta kBT over mu is 125 over 5000, which is 1 over 40. So if I were to look at this function f, if this is mu, at 1 over 40th value of mu, this function comes down. And as temperature is, this is at room temperature. And if the temperature is lower, suppose it's 10 times lower, then this kBT by mu will be of the order of 1 over 40, 1 over 400. So for T equals 300, it's 1 over 40. For T equals 30K, it will be 1 over 400. So it will be even sharper. So the peak is very sharp. The function e raised to epsilon minus mu over kBT divided by e raised to epsilon minus mu divided by kBT plus 1 square has very sharp peak at epsilon equals mu, and is symmetric about epsilon equals mu. So this peak is symmetric. This you can check very easily. So these are the properties of its derivatives. Now let's look at the function del f del E, which was equal to minus 1 over kBT times this f prime. So this is sharply peaked, no problem. Let's look at del f del T, which was epsilon minus mu over kBT square f prime minus d mu dt 1 over kBT f prime. Now I have already said that mu or d mu dt is proportional to t. So the second function is going to be a constant times f prime for t much less than 1. The first function will dominate. Actually, I am not comparing t and or number 1. We should be compare that t over tf. If this is much less than 1, then first term will dominate, and I want you to check that. From this you can also see that integration partial f partial t dE will be almost 0 plus a term of the order of t over tf. Let's check that. More importantly, and related to our work, is that integration partial f partial t density of states epsilon dE is exactly 0. This is very easy to prove. because the number density n is equal to integration f e t dE integrated over the energy 0 to infinity. And if you change the temperature, number density doesn't change. dN dt is 0, and this implies integration partial f partial t dE is 0. With all this in our arsenal, we are now ready to calculate specific heat of free electrons. So now I'm going to do calculation of specific heat of free electrons. Now, as I said earlier, the energy ut, and this is the notation that Kittel uses, is equal to 0 to infinity integration over energy E dE f E t f d, and therefore specific heat CVT is going to be only temperature dependent quantity in the integrand is f. So this is going to be 0 to infinity dE E dF dt. Let me ask you a question at this point. Why is the quantity being calculated Cv and not Cp? Let me also ask you another question. What is measured experimentally, Cv or Cp? So now we want to calculate this quantity. Cv equals integration 0 to infinity dE E dE del f del t. Which I can write as integration 0 to infinity dE E dE, some function times, what is important is that you are going to have e raised to epsilon minus mu over kb t over e raised to epsilon minus mu divided by kb t plus 1 whole square. And we have seen that this function is sharply peaked at epsilon equals mu. So we use that to do a manipulation, and this is a general manipulation in all these calculations involving Fermi-Dirac function. So that trick that we use is manipulate the integral containing f fd e t in such a way that you end up getting either df dt or df de in the integrand. This you can do either by integration by part or something, and once you do that, this helps in performing the integral, because df dt or df de is proportional to Dirac delta function at epsilon f, or you can say Dirac delta function at mu. I'm using Dirac delta function symbolically. What it means is sharply peaked at mu. So let me write that. And what that does is then you can take out a lot of things from the integrand, taking their value at mu, and rest of the integral becomes easy. So we are going to use precisely that here. So we are calculating Cv, which is integration 0 to infinity dE epsilon dE df dt, which is equal to 0 to infinity dE epsilon dE epsilon minus mu over kBt square times that term e raised to epsilon minus mu over kBt over e raised to epsilon minus mu divided by kBt plus 1 whole square. Now you see I have a term which is epsilon minus mu here, another term which is e, and this is sharply peaked at epsilon equals mu. So what I like to do is do a manipulation so that the integrand is in terms of epsilon minus mu. So everything, if it is in terms of epsilon minus mu, then the integral becomes quite easy. Now there are different ways of doing it. Mermin does it using something called the Sommerfeld expansion. Kittel does it in another way. I'm going to do it in another way, and they are all linked. Some steps are very similar. So what I'm going to do now is use the fact that integration dE dE df dt is 0, and subtract mu times this integral dE dE del f del t from the expression for Cv. That is this expression. So I'll bring it over here. When you do that, you get Cv equals integration dE epsilon minus mu dE df dt. I just subtracted 0, so nothing really changes. And when I write it explicitly, it becomes equal to integration dE epsilon minus mu square over kb t square times all that exponential term e raised to epsilon minus mu divided by kb t divided by e raised to epsilon minus mu over kb t plus 1 whole square. That's the term I need to calculate. But now you see everything is in terms of epsilon minus mu. So the integral is quite easy to perform. This integral is obviously energy is varying from 0 to infinity. So I'm calculating Cv, which is equal to 0 to infinity dE epsilon minus mu over kbt square dE times that exponential term. Now I can take out this density of states at mu, because this whole function is sharply peaked at mu. So I can write this as d at epsilon equals mu integral 0 to infinity dE epsilon minus mu divided by kb t square times that exponential term. Take epsilon minus mu over kbt to be equal to x. There is a square here. Then this implies dE equals kbt dx, and therefore I can write Cv as density of states at epsilon equals mu times integral kb kbt dx x square times e raised to x over e raised to x plus 1 whole square. This whole integrand is even, and the integration variable is limits are mu over kbt to infinity. Now recall, mu over kbt even for room temperature is like 40 at T equals 300 K. At very low temperatures, mu over kbt will be even larger, and by that time this exponential has really died down, and therefore the lower limit can be written as minus infinity, and that tells you that Cv is equal to d epsilon equals mu integration minus infinity to infinity kb square t x square e raised to x over e raised to x plus 1 square dx. Which is d epsilon equals mu kb square t times integral minus infinity to infinity x square e raised to x over e raised to x plus 1 square dx. As simple as that. And this integral value is pi square over 3. Please go and look up how this integral is done. It's very interesting. You take e raised to x out and then expand it, and it's an even integral, and then you get a series, and that you integrate. In any case, what you get now is that Cv is equal to pi square over 3 d at epsilon equals mu Kb square T. So, there is one temperature dependence due to Kb square T term, and there could be another due to mu, which is a function of T. However, recall that mu as a function of T, I have already told you, is epsilon f minus pi square over 6 kBT square over epsilon f. So, I can write d at epsilon equals mu equals d at epsilon equals the Fermi level minus d prime times this number, which is of the order of T square. For low temperatures, I can ignore this. This is going to be very small, and therefore, finally I get my expression for Cv, which is pi square over 6, pi square over 3, density of states per unit volume at epsilon f, Kb square T. So, Cv over T is number pi square over 3 Kb square density of states at epsilon f, and this is the quantity which is material dependent. The others are constant, and this is called gamma. So, C electronic is equal to gamma T. It varies linearly with temperature at low temperatures. Let us make some comparisons. So, if I write the value of d epsilon f, so Cv over T is pi square over 3 Kb square. Def is going to be 3 by 2 n divided by epsilon f, which is equal to 1/2 pi square n over epsilon f Kb square, which is equal to 1/2 pi square n Kb square, and I am going to use that temperature for Fermi energy. So, I am going to write this as Kb Tf, where we had defined Tf earlier. So, this implies that Cv as a function of temperature for free electron gas is pi square n Kb T over Tf. Compare this with classical Cv, which is 3 by 2 n Kb. This is given by equipartition theorem, and this is what we had used earlier in Drude model. So, when you use quantum mechanics, you take these free electron wave functions, use the Pauli exclusion principle to fill the Fermi sphere, you get Cv over C classical of the order of T over Tf, which is much less than 1 at low temperatures and even at room temperature. Let us estimate the value of gamma. So, Cv over T is equal to 1/2 pi square n Kb square over epsilon F. This is per meter cubed per Kelvin square, and on top will be joule. Those are the units. Usually Cv is measured in joule per mole K. So, instead of this N, we will use N Avogadro. That will give you Cvt per mole. So, let us do that. I have gamma equals Cv over T, which is pi square over 2. Now, I am going to have an N Avogadro divided by epsilon F Kb square. And putting in our estimated numbers, this is roughly 10 over 2 times 6 times 10 raised to 23 divided by epsilon F. I will take of the order of 5 eV. So, 5 times 1.6 times 10 raised to minus 19 times Kb square, which is 1.4 times 10 raised to minus 23 whole square. So, that is roughly 2 times 10 raised to minus 46 joules per mole Kelvin square. Let us do this calculation. This 5, 2 and 10 go away, and this is roughly 4. So, this comes out to be 8 times 10 raised to minus 4 joules per mole Kelvin square, roughly 0.8 millijoule per mole Kelvin square. So, we will say that gamma is of the order of 1 millijoule per mole per Kelvin square. Experimentally, let us ask this question: how is gamma measured? So, what is done is one measures the Cv and plots Cv over T with respect to T square. This is the graph you are going to see in all books, and you get a straight line. What this tells you is that Cv goes as gamma T plus some other constant T cubed, and this intercept is gamma. The second term comes due to lattice vibrations, which we will talk about in coming few lectures. So, this intercept experimentally gives you gamma. We have already said and estimated that gamma is of the order of 1 millijoule per mole per Kelvin square. Let us see the experimental number for potassium, and that will also help us define something called the thermal mass. For potassium, epsilon F is 2.12 eV, and that is the only number for estimating Cv per mole that is material dependent. So, Cv over T is pi square over 2 n Avogadro divided by epsilon f kb square. So in this case, the number will be roughly 10 by 2 times 6 times 10 raised to 23 divided by 2.12 times 1.6 times 10 raised to minus 19 times 2 times 10 raised to minus 46, and you do the calculation and this number comes out to be 1.66 millijoule per mole per Kelvin square. This is a theoretical value. Experimentally, when Cv over T is plotted against T square for potassium, this intercept comes out to be 2.08. So gamma experimental is 2.08. So gamma experimental divided by gamma theory is 2.08 divided by 1.66, which is 1.25. What causes this? Let us understand that. You see, gamma is pi square over 2 n Avogadro divided by epsilon f kb square, which is pi square over 2 Na over h cross square kf square times 2m kb square. This is given for a material. These are all constants. So the only thing that could differ is this m, and gamma is proportional to m. This implies that larger gamma than gamma theory implies m in a metal is larger than m free, which is 9.1 times 10 raised to minus 31 kg. How could this be? So the reasons could be electron-electron interaction, may make electrons more sluggish, that is, they move slow, implying higher mass. Similarly, other thing we have neglected is the electron lattice interaction. May also make electrons slow to respond, because anytime there is an interaction, for example, you are walking, but if you are interacting with a lot of people, your walk becomes slower. So the electrons may move with little higher inertia. So this may give a higher mass. So we defined through this something called the m thermal or thermal mass, which is equal to gamma experiment divided by gamma theory times m.e. You will see tables in Kittel or in Ashcroft Mermin that if you look at Cv, they also quote thermal mass. So thermal mass for potassium is 1.25 ME. Let me now conclude this lecture by stating that we have calculated Cv for metals using free electron model and derived an expression for it. And then we have defined thermal mass of an electron in a metal by comparing gamma experiment and gamma theory. Thank you.